Hello everyone. The topic of this seminar is three-phase semiconverter. It's also called as three-phase half converter, also called as three-phase half controlled converter. It is a single quadrant converter, which means the output voltage and output current, they are always positive. And the three-phase semiconverter or three-phase half bridge converter, which employ three thyristors, three diodes that are connected in the form of bridge configuration. Three thyristors are control switches and the three diodes are uncontrolled switches. And the diodes will conduct as soon as they are forward biased by the respective phase voltages. The three-phase semiconverter, it can be used in the industrial power applications up to 120 kilowatt. The power level where the single quadrant, it can be used up to 120 kilowatt power level where the single quadrant operation is required. The thyristor T1 is forward biased when the phase voltage VA is more positive, and diode D4 is forward biased whenever VA is more negative. Similarly, T3 is forward biased when VB is more positive, and D6 is forward biased when VB is more negative. And thyristor T5 is forward biased when phase supply voltage VC is more positive, and diode D2 is forward biased when the phase voltage VC is more negative. The angle 30 degree, which is called as natural point of triggering, this is the angle from which the firing angle alpha is measured in order to trigger T1. So from this angle, from this natural point of triggering, we have to measure the angle, firing angle alpha to trigger T1. And we can trigger T3 after 120 degree interval and T5 again after 120 degree interval. Then when T1 is triggered at alpha, we can trigger T3 at alpha plus 120 degree, and we can trigger T5 at alpha plus 240 degree. At any point of time, the load current, it would flow through one upper device and one lower device. Hence, the load voltage will follow the line voltage. And the circuit, which is semiconverter circuit, it has a inherent freewheeling action, because of which it is able to give only first quadrant of operation. Let the phase voltages be VAN equal to Vm sin omega t, which we are going to take as reference. VBN equal to Vm sin of omega t minus 2 pi by 3, which means VBN lags VAN by 120 degree, and VCN equal to Vm sin omega t plus 2 pi by 3, or it can be written as Vm sin omega t minus 4 pi by 3, which means VC. The first waveform shows the line voltage waveform, and the second waveform shows the first waveform shows the phase voltage waveform, and the second waveform shows the line voltage waveform. VAN is the reference voltage, so it is drawn from 0 degree. And the VBN, it starts from 120 degree after VAN. Again, VCN starts from 240 degree from VAN. So these are all, the second waveform is the line voltage waveform. Now we will see what is the output voltage when different combination of devices conducting. When T1 and D6 they are conducting, we will get the output voltage that is equal to VAB. When T1 and D2 combination it is conducting, the output voltage will follow VAC. When D2 and T3 are conducting, the output voltage will follow VBC waveform. When T3 and D4 are conducting, the output voltage will follow VBA waveform. When D4 and T5 combination is conducting, the output voltage will follow VCA waveform, and when T5 and D6 are conducting, the output voltage will follow VCB waveform. So at any time, when two devices, one from top and one from bottom, are conducting, the output voltage, it is going to follow only the line voltage waveform. So we need to consider only the line voltage waveform as shown here. In the line voltage V waveform, we have VAB, VBC and VCA. In order to get VAC waveform, we have to draw the VCA waveform in the opposite direction, so that this portion will be drawn in the opposite direction to get the VAC waveform. Similarly, this portion will be drawn in the opposite direction to get the VAC waveform. In the semiconverter, since the output voltage is always positive, we have to take only the positive side of all the waveforms. So again, we have VBC waveform. In order to get the VCB waveform, we have to draw the negative VBC waveform in the positive side as my mirror image to get the VCB waveform. Again, for VAC waveform, we have to draw the VCA waveform as a mirror image to get the VAC waveform. Then we have the VAB waveform. If we draw the negative part of the VAB waveform as the mirror image, we will get the VBA waveform. The diode which is connected to C phase, it will be turned on automatically. So in the next stage, T1 will conduct along with D2. So this is the circuit during which T1 will conduct along with T2 after this point. So after this point, D2 is forward biased. So T1 will conduct along with T2. Therefore, the current will flow from A phase through T1, through the load, through D2 and back to C. Now the load is connected between A and C terminals. So the load voltage, it is equal to VAC. So load voltage will follow the VAC waveform. This process will continue until the next thyristor T3 is triggered, which is triggered at an angle which is equal to alpha plus 120 degree. So when T3 is triggered, T3 will conduct. When T3 is triggered, T3 will conduct along with already conducting diode D2. So the load which is connected between B and C terminal, so load voltage is equal to VBC. And at this point, D2 is turned off automatically, and D4 it is now forward biased by the A phase, which is more negative during that time. So D4 will come into conduction. So after D4 is conducting, T3 and D4 combination will conduct. Hence, the load current flows from the point B through T3, through the load, through D4 and back to A. Therefore, load is connected between the terminals B and A. So the load voltage V0 is equal to VBA. Next, T5 is triggered. When T5 is triggered, T5 will conduct along with D4. So current will flow from C through T5 through through the load, through D4 and back to A. So the load is connected between the terminals C and A, hence load voltage is equal to VCA. After this point, D4 is turned off automatically. Therefore, T5 will conduct along with D6. So current will flow from the point C through T5, through the load, through D6 and back to B. Hence the load is connected between the terminals C and B. Hence the load voltage is equal to VC. So this process will continue. Again, when T1 is triggered, it will follow VAB, then VAC, then VBC, then VBA, and so on. Now, this is the load voltage waveform. The load voltage waveform is shown by the darkened black line. So for alpha equal to 30 degree, that is firing angle equal to 30 degree. So from the natural point of triggering, alpha is measured and it is taken as 30 degree, and T1 is triggered. When T1 is triggered, it will conduct along with D6. So the load voltage will be equal to VAB. Then it will conduct along with T2. So load voltage is VAC. When T3 is triggered, load voltage follows VBC. Later on, when D2 is turned off, it will T3 and D4 combination will conduct, so it will follow VBA. When T5 is triggered, T5 will conduct along with D4, during which the load voltage follows VCA. Then at this point, when D4 is turned off, D6 will conduct. So T5 and D6 combination will conduct, during which the voltage is equal to VCB. Before T1 is triggered, the combination of 5 and T5 and D6 were conducting. So during that period, the load voltage is VCB, which is giving the output voltage following the waveform VBC. Later on, VBA, the output voltage will follow VBA, then the output voltage will follow VCA, then the output voltage will follow VCB. Now, this is the waveform for alpha equal to 60 degree. So, for alpha equal to 60 degree, we have to take the alpha from this natural point of triggering. You have to measure 60 degree from this point. So, alpha 5 by 6 plus alpha will be here. At this point, T1 will be triggered. When T1 will be triggered, T1 will conduct along with the D2 combination. So T1 and D2 will conduct. So the output voltage will follow VAC waveform until T3 is triggered. When T3 is triggered, T3 will conduct along with D4. So the output voltage will follow VPA. Then T5 is triggered, which will conduct along with D6. So the output voltage will follow VCP. Similarly, before T1 is triggered, T5 and D6 combination would have conducted, which resulted in the voltage VCP. So at alpha equal to 60, we cannot have the combination of T1 D6 combination, because at the point of triggering of T1 itself, the voltage which is connected, that is diode with D2, which is connected to the C terminal, it is more negative. So diode D2 will conduct automatically. At that time, D6, during this time, it would have turned off even before your T1 is triggered. So we will not get the combination of T1 and D6 combination when alpha equal to 60 degree and more than 60 degree. Now we can derive the average voltage expression taking the alpha equal to 60 degree waveform. So for any voltage waveform, we can see here that for one full cycle, there are 3 pulses being produced at the output. So this converter is also called as 3-pulse converter. So we can find the average output voltage as, since we have 3 pulses at the output, we can take 3 by 2 pi. And we can integrate the waveform from pi by 6 plus alpha to this point. So this point is nothing but 7 pi. We can find the average output voltage by integrating the AC between pi by 6 plus alpha to 7 pi by 6. So during that time, the V0 follows VAC waveform. So we can take a VAC equation and we can integrate that between the limits pi by 6 plus alpha to 7 pi by 6. We know VCA equation, VAC equation can be written like this. So root 3 Vm sine omega t minus pi by 6, we have to integrate between the limits pi by 6 plus alpha to 7 pi by 6. If we integrate that and substitute the limits, we will get the expression which is equal to 3 root 3 Vm by 2 pi cos alpha minus cos 180 degree. We know that cos 180 is plus 1. So the final expression for average output voltage is 3 root 3 Vm by 2 pi into 1 plus cos alpha. This is the average output voltage of the three-phase semiconverter. So from this expression, we infer that for alpha equal to 0, we get a maximum average output voltage as the alpha is changing from 0 to 180 degree. The output voltage waveform, it decreases from the maximum value towards the zero value. So we will take the average output voltage varying from the maximum value to zero value. We will not get any negative average output voltage. Hence, this is a single quadrant converter. Thank you.